Today we're going to look at another example problem where we are calculating both phase and temperature, or phase and thermal energy changes. The very most important part of these problems is the very first step, making your graph, because that's where you plan what steps you're going to have to take, what calculations you need to do. So we're going to make our temperature versus energy graph for every problem first. In this problem, we're going to start below zero at a temperature of -5 degrees Celsius. And there are no phase changes that take place at this temperature, so as we add energy, the temperature is going to start going up. But there's going to be a point where the temperature won't go up because a phase change is going to occur. And the first time that we encounter one of those places is at 0 degrees Celsius. At this temperature, we're going to see a phase change. The temperature and the thermal energy will stay the same. Then, once all the ice has melted to liquid water, the temperature can start to climb again, and it will climb until it gets to the next phase change point, which happens at 100 degrees Celsius. At 100 degrees Celsius, water changes from a liquid to a gas. So we'll have another place where the temperature doesn't change because the energy is being used to spread those particles further apart as they transform from a liquid into a solid. Once all of the liquid has evaporated, then the temperature can start to rise again, and it will rise up to the final temperature of 110 degrees Celsius. Once I have the general shape of the graph, I can see really easily there's 5 different sections to this graph, so I'm going to have 5 steps in my calculation. And I'm going to go through and plan what constant I need to use in each section of the graph. All of the slanty parts of the graph are temperature change regions, and in temperature changes we're going to use the specific heat or heat capacity, which is the energy that it takes to change the temperature by 1 degree for 1 gram. So I'm going to label each of those sections with C. Now I also want to remind you the heat capacity is not the same for a solid, a liquid, and a gas. So below 0 degrees we're going to use heat capacity for a solid, because water is a solid in that range. Between 0 and 100 degrees, water is a liquid, so we'll use the heat capacity for liquid water. And above 100 degrees, water is a gas, so we'll use the heat capacity for a gas. In the phase change regions, we either use heat of fusion or heat of vaporization. At 0 degrees, where water changes, either melts or freezes, we use the heat of fusion, HF, and I remember that because F is for freezing and fusion. At 100 degrees, we use the heat of vaporization, and an easy memory tool for that is V is for vaporization, and vapor is another name for a gas. So we now have our 5 calculation steps plotted out, and it's time to get started. So step number 1 is a temperature change, and it is going to use the heat capacity of solid ice. I will always give you the heat capacities and the heat of fusion, heat of vaporization for whatever substance that you're using, or I'll give you enough information to calculate it if it's a problem where I want to know what the heat capacity is. So the heat capacity for solid water is 2.1 joules for every 1 gram to go up 1 degree Celsius. But when I look at this problem, I want to know how many joules of energy are required to take not 1 gram, but 75 grams. And I don't want to change the temperature just 1 degree. I'm going from -5 to 0 degrees Celsius, so the temperature is going to change 5 degrees Celsius. To solve this, I'm going to cross multiply. So 2.1 times 75 times 5 equals 1 times 1 times x, which is just x. So x equals, I'm going to punch those numbers in my calculator. And when I did that, I got 787.5 joules. I'm going to hold off on my rounding until the very end of all this process. So now we're on to step 2, which is a phase change. At step 2, we're using heat of fusion, and this is the phase change where the solid water transforms into liquid water. So energy is being used to separate those particles and allow them to slide past one another. The heat of fusion of ice is 334 joules for every 1 gram. But we don't have 1 gram, we have 75 grams, so we need 75 times as much energy. And so we're going to calculate how much energy we need for 75 grams. Again, we got a proportion, one fraction equals another, so we're going to cross multiply. 334 times 75 equals 1 times x, where x equals, and I got 25,050 joules. Again, I'm going to just hang on to that number and not round until I get to the end. Step 3, we're going to use the heat capacity of liquid water, because in step 3, that's our next section of the graph. Liquid water's heat capacity is 4.18 joules for every 1 gram of water to increase in temperature 1 degree Celsius. But again, we're not dealing with 1 gram here. We've got 75 times as much material. And in that third region of the graph here, we're going from 0 degrees Celsius up to 100 degrees Celsius. That's a change of 100 degrees. So the temperature is not just going up 1 degree, it's going up 100 degrees. And we want to know how much energy that's going to take. Cross multiply 4.18 times 75 times 100. And I got that x is equal to 31,350 joules. So that was step 3. We're almost there. Step 4 is heat of vaporization. This is now the phase energy is changing. Its energy is being used to rip those particles apart, spread them way out so they've transformed from a liquid to a gas. The heat of vaporization of water is 2,260 joules required to evaporate every 1 gram of water. But instead of 1 gram, we have 75 grams. And we want to know how much energy that takes. So cross multiply 2260 times 75. X equals 169,500 joules. That's quite a bit. And I don't know if you've noticed it, but actually the 2 phase change steps, step 2 and step 4, use a whole lot more energy. And that is generally the case. It generally takes a lot more energy to change the phase of something. Finally, step 4, still got to go up 10 more degrees to complete the story in the problem. So we're going to go from 100 degrees up to 110 degrees, which is a temperature change of 10. You notice I'm not using the whole 115 degree temperature change in every step. I just use the temperature change in that step. So for this one, it's just 10 degrees. The heat capacity for a gaseous water, is 2 joules for every 1 gram to go up 1 degree Celsius. But as is the custom, we didn't have 1 gram, we had 75 grams. The temperature did not just increase 1 degree Celsius, it went up 10 degrees Celsius. And we want to know how much energy that takes. So cross multiply 2 times 75 times 10. And I got 1,500 joules for that last step. So now we need to figure out the total amount of energy. We know the amount of energy for each individual step. We're going to add it all together. So back to the beginning, we're going to add 787.5, 25,050, 31,350, 169,500, and 1,500 joules all together to get the total amount of energy needed. And I'm going to use Q because Q is that process of energy being transferred in or out of a system. Q total is, if I added those together, I got 228,187. Now here, finally at the end, this is where I'm going to round. If I go back to my original problem, I've got 2 sig figs, 1 sig fig, and 2 sig figs. So my answer should have one significant figure, so it's going to round to 200,000 joules. And the last step is I've got to decide, did energy enter the system or exit the system? Well, looking at my graph, it goes up as time goes on. We've added more energy and the temperature is increasing. The phases are going from solid to liquid to gas. So this is an example where energy was added. And because energy entered the system, we could also classify this as endothermic or exothermic. Energy entering a system is endothermic. Endo-enter. And just as a reminder, you can do each individual one-step problem just like this, and I could ask you on a one-step problem to solve for energy, to solve for mass, or to solve for temperature.